So it's great to be here. So a year ago, I was presenting at NICE for the first time on our Loihi chip, basically unveiling it to this group. So I thought I'd be able to skip over all the sort of introductory material until I saw all the hands yesterday of people here for the first time. So I'll try to go quickly through some very basic intro material. So first of all, just sort of setting the stage on sort of our perspective and view of this field. And sometimes this kind of three-circle Venn diagram, I think, is a nice way to visualize it. In particular, the relation to deep learning, which is oftentimes very confusing, a little bit nuanced, and a lot of people make the wrong assumptions about this. So first of all, in terms of these, you can kind of barely make out the colors, but the main color here, this kind of what is that? Pink color, I guess, competitive computer architectures. So at Intel, we're in the business of building chips that we can sell to solve a wide range of problems. Programmable chips, not necessarily ASICs that solve singular problems well, but broad architectures that enable many competitive applications. Today, of course, we have the rise of intelligent computing, whatever that may be. Deep learning, of course, being a major driver of that, machine learning generally. And so machine learning naturally is a source of inspiration for how we can define new architectures and new programmable chips to address these new needs. And by machine learning here in this top left, I don't necessarily mean a specific set of algorithms, but it's more a approach to algorithm discovery. So a way to find algorithms, programming models that allow you to solve problems in a very deterministic, well-defined manner. So it's very mathematical. You start with some kind of objective function, a loss function, you define an optimization procedure, and you arrive at something which you know will solve a particular problem, given certain assumptions and inputs. So it's great. On the other hand, there's sort of an assumption built into this that you have a programmable architecture underneath it that's going to run it. Because whatever mathematical expression you arrive at, whatever algorithm, the assumption is that you can run this in some way or another. And so in some ways that requires some kind of a von Neumann programming model. So that's not necessarily where we want to look. And plus it relies on human inspiration without any particular guide to something that we know will be efficient. So that's where this brain-inspired computation comes in, or neuroscience, where we have a model of something that actually works in nature. In fact, every one of us has that in our own head. And the energy efficiency is incredible. The speed that we can perform inferences and learning is incredible. And so this is, of course, another great source of inspiration, and it's guided computing for back to the greats von Neumann and Alan Turing, as we were talking about yesterday. So that's another great source of inspiration. And if we look at deep learning today, the artificial neural network model, as it's now being deployed and changing the world, really, that sits in this kind of trifecta region. It certainly began as being neuroscience inspired, this artificial neural network model, although even at the time, 50, 60 years ago, it was understood to be a pretty crude approximation of a neuron. But nevertheless, it's become very, very useful and surprisingly powerful. But it's only gotten there for a couple of reasons. But part of that is because of the backpropagation algorithm. So a method of actually tuning and training these networks offline, right? So given a large amount of data, you can apply this algorithm and you can actually make these deep neural networks useful. But that's not a neural-inspired idea. That is truly coming from the machine learning direction. It's stochastic gradient descent, chain rule derivatives applied to this mathematical construct. And the surprising thing is it actually works really, really well. But we're interested at Intel more than necessarily this region here and just doing a better job at deep learning, but really expanding the space of the types of computation that our neural-inspired computational architectures can support. And that's what we see as the spiking neural network model, in conjunction with many other principles that we find in the brain and in guiding neural computation. But it's truly a broadening of the space of possible computation. That's what we find very inspiring, and that's kind of the goal we're working towards. I've listed here on the right some example algorithms of what we think we can enable. Of course, many of those relate to learning, so much more energy efficient learning, data efficient learning, without needing to send all the data to the cloud. But there's other algorithms here as well. So things that people don't necessarily commonly associate with neural networks. So things like sparse features extractions, constraint satisfaction, performing probabilistic inferences and Bayesian type of computation, navigating, SLAM and planning types of tasks. So there's a lot of interesting things that we find happening in the brains that neurons are clearly computing at great efficiency. I mean, you see a mosquito doing some of these types of computation that just fall outside of the domain of deep learning. So this is something that we're hoping to be able to uncover a general purpose architecture that can support all of this in a programmable way. So this is where we need this broad class of algorithms. Of course, there is this intersection here with deep learning, and so that's where a lot of the confusion arises. So the spiking neural network model is really, in most respects, it's a generalization of the behavior. It adds time to this artificial neural network model in a sort of a simple, principled way. And, but it does mean you can encode data and perform similar computations with spiking neural networks as you can with ANNs. And so for that reason, there is this intersection here, which is interesting, not necessarily the sweet spot for the technology, though. So it's something to keep in mind. Ultimately, efficiency is what we're looking for here. I mean, as we know, a Turing-complete processor, whatever form it may take, can run basically anything except maybe a quantum program in polynomial time. So really, ultimately, what we're dealing with is an architecture that can provide great gains in efficiency compared to the architectures we are familiar with today. Another interesting property that we find particularly interesting at Intel, a company in the business of Moore's Law, is the scalability of neural architectures. So the fact that you have everything from a 300 neuron nematode worm brain in nature up to 80 billion neurons in a human brain. And this is the basic same ingredients, axons and neurons and synapses that just get scaled up. And as you add more and more neural resources, you get more and more powerful computation while maintaining incredible energy efficiency. And that is not something we find in conventional computing outside of maybe something as boring as memory. But this is doing computation as well. Okay, so that's kind of our perspective. Here's just some examples of what I mean by principles, neural computational principles that we see. So on the one hand, we have this fine-grained, probably the most defining characteristic of neural computation is fine-grained integration of memory and computing. So you don't have this von Neumann kind of idea of this divide between a memory architectural element and a computing architectural element. These two architectural elements and the very concept are completely integrated. Memory is distributed with the computation. The connectivity in neural networks found in the brain are incredibly different from anything we would either map in deep learning networks today or certainly what we find in chips designed today. So fan-out factors of 10,000 routinely. So each neuron connecting to 10,000 other neurons. Our typical circuits would connect to, say, a factor of 10 fan-out. And what's more is these recurrent loops of activity. So you have feedback on all scales, which is, again, something that we find absent in our traditional chips that we design, as well as most deep networks as well. So secondly, neural systems compute with time, which is kind of not something we normally think of. We think of computation requiring time, and the minimal amount of time, the better. But actually, neural circuits, spiking neural networks in particular, will use time as a fundamental kind of dimension in the computation, an independent variable here. And so therefore, you naturally get a dynamical system, and the computation is actually happening through the evolution of the system over time. It's not necessarily how fast or slow it is, it's just what it's doing through the course of time. Of course, low precision, stochastic computation, these are ideas that are a little more familiar to the conventional machine learning domain. And then finally, we have adaptive self-modifying nature of neural tissue, which is not just necessarily weights at the synapses, but all sorts of parameters in these networks which are changing continuously over time over a variety of different timescales. So some of these have all been talked about yesterday. This is, again, just kind of introduction to what we're trying to harness and kind of map into chips that we can build today. Now, the one principle or characteristic that gets a disproportionate amount of attention that we started talking about yesterday was this question of spikes. And we looked at that very early on, about 4.5 years ago when we started this research program at Intel. And we found some interesting characteristics of spikes. And as we got deeper and deeper, we found more and more evidence and more confirmation that this is a productive path to pursue, is to build chips that actually spike in some way. Now, by spike, we don't literally mean what a biological circuit is doing, which is a blip of voltage, an action potential, but more an abstraction of that. So it's an event-based packetized message, which is getting sent between neural computing elements in this architectural system. But the key idea is that it's not conveying data necessarily. It's only conveying addressing. So which neuron is connecting to which other neurons and the timing of that event. When is the activation of a neuron hitting a particular threshold? That timing is critical. And then the particular neurons that it connects to is also critical. So we found a variety of reasons that support the efficiency that, if you ask a neuroscientist, they say, well, spikes are there for some sort of efficiency reason. We may or may not need it to explain the operation of the brain, but clearly there's, some reason for it from an efficiency standpoint. So I'll go through the data, the results that support these conclusions, most of them anyway. But I think hopefully by the end of the talk you'll agree that well, there very well does seem to be something to this. It does actually deliver gains in efficiency. The first one I won't go into in any detail, but it's actually just a very simple result that comes from information theoretic analysis. That conventional information theory is about maximizing the utilization of a channel, so the bandwidth given a fixed constraint of a capacity. As soon as you add an energy penalty to communicating, and you have an asymmetry between sending something versus not sending something, you immediately get a preference for sparse activity. So you don't want to be sending at 50% of the channel bandwidth, which conventional information theory would tell you to do. Instead, you want to prefer the off state. So that effectively tells you that if all algorithms are otherwise equal, you should choose the ones that involve sparse communication, or that spike, basically. So naturally, nature has found ways to find algorithms that get the job done using sparse communication. So we should probably do that too in our hardware architectures. So secondly, spikes efficiently compute many rate-based models. So this is kind of a counterintuitive finding, but I'll go through an example that kind of really nicely illustrates this kind of false dichotomy between rate-based models and spike timing-based models. Certainly, if you're familiar with this, many would instinctively regard a rate-based model as being inefficient because you think, well, you have to send many spikes to achieve a certain rate, an average rate. And so therefore, we should dismiss all of those class of models because they're not going to be efficient on spiking neural network model, and who knows why the brain may use such coding strategies. Well, it turns out that actually these can be very efficient in neuromorphic hardware, and I'll explain why. For temporal data in particular, even for the most simplest feed-forward types of networks, if there's temporal structure in the data stream, you can actually also get gains using spike-based computation. So we'll show another example of that. And then finally, there is a whole class of algorithms that fall outside of the domain of what we would normally regard as kind of neural network, rate-based, kind of define some derivatives and nonlinear activations and these sorts of approaches. And that really just cleverly use the event-based timing encodings of spikes and some of the dynamics that can arise and perform novel computation. So I'll give an example of that. And then finally, kind of the most recent result here is something about phasor networks. So hopefully I'll get to that. But this is basically an interesting abstraction of a neural network model where you associate a complex number with every neuron activation. And this has been explored for quite some time in the context of deep learning. Advantages have been found for this class of type of neural network, but it seems more kind of esoteric and exotic. Why would you necessarily go to the trouble of doing computation with complex numbers? It turns out that when you look at a spiking network implementation of this, those complex numbers correspond to oscillatory interactions and oscillatory states. And so we have some examples of that type of a network, and that gives you automatic sparsity of activation once you have oscillating spiking processes, as well as very interesting interaction possibilities through coupled oscillation and these sorts of things. And so that we believe will give great efficiency, and we have some early results in that class. So overall, all of that requires spikes and is giving us great gains, and not just small gains. I mean, even this first one, this information theoretic analysis, it just doesn't go beyond a factor of 10 or so. It's probably around a factor of 4. But still, in the context of conventional compute, where percentage gains are important, multiple factors, even just from a single ingredient here, is pretty notable. Okay, and also I'll point out, and as you'll see, that as you go to larger networks, what we've almost in every case found, that the gain when we benchmark compared to a conventional programmable architecture, the gain for the neuromorphic architecture gets better and better as you go to larger networks, which is also something we find very interesting. Okay, so with that all background, most of you, I think, have probably heard about our chip, Loihi. So we published this over a year ago now. If you want to know about the chip, this paper is in IEEE Micro and give you a nice introduction. Or come to our tutorials on Friday. We'll go through a lot of the internal detail that I'm not going to have time to go over now. I'll try to hit just the key aspects of it so the rest of the talk makes sense. So first of all, this is a fully digital chip. I've heard a lot about analog neuromorphic chips. People are looking at memristor neuromorphic chips as the future, perhaps. We chose to just stick with known manufacturing technologies, very conservative design techniques, because we're much more interested in exploring the architectural space and getting the architecture right. And analog circuits, in our experience, are really painful and take a while to design, hard to iterate quickly. And for that, if no other reason, we've chosen to do this completely digitally. We've actually done 4 chips in this series already. We did 4 chips in 3 years, really just trying to rapidly get the architecture right, strike the right balance between flexibility, programmability, and integration and efficiency. And we hope we've kind of hit that sweet spot with this chip, at least close to it. We're working on the next chip already, so this is not the final answer by any means, but we do think that it's far enough, it's mature enough that we're able to actually deliver and demonstrate compelling computational gain. It's a many-core architecture, so it has 128 neuromorphic cores, all tied together in a dimension order routed mesh NOC network here. It's fully asynchronous, so that is probably the most exotic thing about how we've designed this. So it's at the finest level, there's handshaking between all the pipeline stages in this circuit. This is gives us a nice match to this kind of normally off state that neurons should prefer, spiking neurons should prefer. We've got a very advanced neuromorphic feature set. So from a spiking neural network perspective, leaky integrated fired neurons. We have even things like dendritic trees you can construct, so you can build more complex neurons out of these simpler neurons. We have homeostasis. We have a lot of work went into the connectivity architecture for this chip so that we can try to, as well as possible, achieve this biological fan-out capacity of 10,000 to 1. We have networks that have pervasively 2,000 to 1. 10,000 is pretty challenging with today's manufacturing technology, but at least we can get up to factors of about 2,000 to 1. We have variable precision weights, so we have anything from 1-bit to 8, 9-bit signed weights. We have multivariate synapses, so we've expanded the notion of a synapse being just a weight to including ideas like tags for reinforcement learning, kind of eligibility traces. We have delays associated with the synapses. Long list of features, so I'll again go into them on Friday. But probably more important than anything else is the learning capabilities. So we've integrated a microcode programmable learning architecture here in kind of a way that respects the neuromorphic architecture in the sense that it's distributed throughout the mesh so that the learning can be local, efficient, and scalable. So I'll talk more about that in a sec. The chip's been manufactured in 14 nanometer FinFET, so the same process technology that we use for all of our Xeons and Core chips in your laptops. So the manufacturing technology completely standard. This is probably 80–90% of the design to the standard of something that could be mass produced. It's not 100%. This is definitely not a product. It is a research chip, but the approach, the methodology we've used could lead to a chip that we could sell and produce in mass volume. Okay, so briefly on the theory of operation, just what's going on under the hood. One thing I didn't mention is that Loihi is fully deterministic. It came up yesterday that this is really nice from a software development perspective, if nothing else, is to have deterministic operation in the chip. You program it one way, you feed it inputs, it's always going to give you exactly the same outputs if you give it those same inputs. Yet, the design is 100% asynchronous. So that some people scratch their heads and find that a little bit hard to understand. This mechanism here kind of explains how that works. So we go through this synchronization process where we disconnect the idea of time in real-time operation of the chip and the algorithmic time of the neural computing model here. So we have something called algorithmic discrete time steps. As a user, you just look at this as a discrete time leaky integrated fire neuron system. No matter how big the system is, how many cores you're using, or even how many chips you're using. Loihi, by the way, is scalable to many chips. As a user, you just think about discrete time. You can even think of it as being clocked, even though we're not clocking the system. You can think of it as just stepping through time, the t+1, t+2. So the system begins on the left here, idle. So no spikes, nothing. Each of the cores, though, implements in a time multiplexed way the state for 1,024 neurons, up to 1,024 neurons. So all of these cores are walking through all of that state, updating the dynamic state variables, and determining, okay, on this time step t, has this neuron exceeded its activation threshold such that it should generate a spike? And so the second panel is showing that 2 neurons here in 2 cores, red and blue, do that. They generate spikes, they get sent through the mesh to wherever they need to go. That's happening for all of the neurons in those 2 cores here. So you see many spike messages getting generated, and that's actually happening throughout the mesh, so lots of spike messages. This is all applying to the current algorithmic time step t. So in fact, there's no ordering requirements whatsoever on all these spike messages that are getting generated. So in some sense, it's non-deterministic in how the mesh is operating on this fine temporal scale. What happens, though, is that once each of these cores is done with the current time steps of work, they've generated all the spikes they're going to generate, they start handshaking with their neighbors. So that's what this final step here is. I don't know why that's still red. That's odd. But it goes through what we call a barrier synchronization step, inspired from parallel programming, where we now get this wavefront of synchronization that kind of percolates through the system, flushes out all the spikes in flight, such that now we can return to this first step and carry on again. So that means that all the spikes generated in a given time step, as long as they're to be serviced at some time step t+1 or the future, they can all be deterministically handled. They go where they need to go. We can even pipeline these phases a little bit so that we can wash out some of the overhead of the barrier synchronization. And what that gives you is that over time, if you're just performing some abstract computation, you want the answer to some inference as fast as possible, and you don't really care about a neurosecond operating on a neuron operating on a millisecond time scale, say. You just want an answer as soon as possible. That'll happen. You just barrier sync away as fast as the computation allows. If there's not a lot of work to be done, not many spikes on a particular time step, that time step will happen very quickly in real time. Otherwise, it may take a lot more time. And then every so often, what we call the learning epoch, we intersperse a learning operation, so a learning phase. And that's typically on a pretty fine granularity. It could even be every time step if you really want 100% precision in your learning rules. But typically you'd relax that for efficiency out to 4 to 8 time steps. And what that does, this kind of red bar here, is it's servicing some kind of transitory state, activity state that's been maintained in all of the cores, all the synapses and axons, neurons, so that then it can apply those programmable learning rules, update all the neural state variables that are plastic and then carry on. So that's how we do learning. A little more on learning. So the principle here, again, it's one of these basic principles we see from nature. Really, it's even more fundamental than that. It's a basic property of physics, I would say, that computation is local. And scalable computation should maintain that property. So one of the challenges with the von Neumann computing model is it hides that reality. So you can access any address location you want in your program, and you have no clue necessarily, unless you're a ninja coder. You don't know where in your memory hierarchy that's going to correspond to, how far away from whatever core, whatever chip that you're on, and that leads to potentially great inefficiency. Of course, it's really nice from a programmer perspective, so it's definitely a good feature. But from the standpoint of scalable algorithms, it's problematic. In particular, backpropagation is not a local learning algorithm. And so for that reason, backpropagation is not scalable, not very efficient, compared to algorithms that do respect this locality requirement, such as the algorithms deployed in our own brains. So that's the restriction that we imposed and adopted in the Loihi architecture, taking a little bit on faith that, okay, users can figure out what these learning rules are, and when they do satisfy this locality property, then they'll be scalable and they'll be very energy efficient and high performance at scale. So what that means, in terms of this cartoon diagram here, is if you're going to change this weight xy, input arriving from x to the synapse, y is the postsynaptic neuron there, you don't get to access any of this other state in the network. So from other neurons, other synapses, any error signals on the output necessarily, you don't automatically have that visibility because that's somewhere else in the network. The data flow through the neural network is literally the data flow in the chip itself as programmed. So that is a pretty stringent requirement. And luckily, there's a lot of great work going on in computational neuroscience of trying to uncover what are these rules that if you only have access to a tiny bit of state here, perhaps also with, say, a reward mechanism, some kind of neuromodulatory distribution, which we support that in Loihi, then with a limited number of local state variables, how do you get emergent learning behavior with simple local learning rules? So there's a lot of work that's going on in that, and we've defined Loihi's learning architecture, this sort of limited amount of programmability to it, to try to support these sort of cutting-edge learning rules that people are exploring, and some of which certainly work and are being demonstrated today. So that's the other aspect here that I haven't mentioned is this timescale matter. So learning is happening on multiple timescales. There's some of these rules that people are characterizing and looking at, in fact, integrate the same variables, just sort of integrated over different timescales. And these actually, that's important to have, all this range of different timescales. So we have that too. This is kind of a summary in a way of just to try and illustrate, what this actually looks like. This is kind of the deepest I'll go about the internals of the chip in this talk. Here we're back to this diagram of you have this input arriving at this synaptic weight W, and then the output is the blue there. And you can see that if this is all you have, are spikes arriving on the input, spikes in the postsynaptic terminal, what can you do? You can filter them. And so, in fact, that's what's happening pervasively in neural networks in the brain. So that's the basic model. We call this a trace. Once we filter these spikes, that's now a trace, which is a continuous curve. And there's an impulse on every spike, and it decays away. And what you can have are two knobs here. You can control the time constant of the filtering, and you can control the impulse value, how much you're spiking up on every spike. And if you're maxing out the impulse and the time constant is fast, then that puts you into the so-called SDDP regime, where the trace value, that value of the continuous curve, is basically just giving you a measure of how much time has elapsed since the most recent spike. So that's the short time scale interaction correlations that you look at. So that's the typical B and POO SDDP curve. That's that world. Now, on the other hand, you can configure a sub-maximal impulse value and a long time constant. And now what happens is these trace values will accumulate from spike to spike to spike, and you get something that looks like more of a long-term average measure of rate activity. So this architecture unifies the idea of precise kind of short timescale temporal dynamics of spike timing, as well as the rate averaged dynamics of some of these rate models. And then ultimately what our kind of microcode does is it just allows you to specify an equation. You get to build out kind of a sum of products form of learning rules, where you have access to all of the variables that are right at that location, meaning the input traces filtered in different ways, perhaps the output traces filtered in different ways, reward traces, the weight itself, these other synaptic variables like delays and tags, so you can build more complex dynamics in each synapse. And ultimately, that's what you get. With that kind of basic architecture, you can build a surprisingly broad range of learning rules. So things like triplet STDP, as well as simple STDP, heterosynaptic decay, reinforcement learning, kind of eligibility trace-based rules, and a lot of interesting things. So that's all introduction on the chip. Now we'll shift gears. We'll talk about what we've done with chip in the last year or so that it's been out. We've built a number of systems. So this was way back last year at NICE. This is pretty much all we had, which was a bring-up test board. We went on to build a 32-chip board, which plugs into an ARIA 10 dev kit. And so that allows you to plug this board in. The ARIA 10 ARM CPU serves as the host in the system. And then you can go and configure all of these Loihi chips in the mesh. By the way, I didn't mention, but we also have 3 embedded x86 CPUs in every Loihi. So really what you have with this kind of Nahuku system is a big heterogeneous computing system where you have the ARIA 10 ARM CPU, you have x86 CPUs embedded through this Loihi mesh, as well as, of course, a ton of neuromorphic cores across all of those Loihis. And as well, you have something we call the superhost, which is the computer that as a user, you're actually logged into, you compile your networks, and you do your visualization and coding on the superhost. So it's a heterogeneous kind of event-based, channelized, sort of model system architecture of how we built these all out. Then we went on and we built a small system. So this USB system we call a Kapoho Bay. So that you'll see on Friday. You can plug that into a laptop and run the SDK locally on your computer. It has a DVS interface, so an AER DVS interface for the INI Labs Davis 240C camera. So if you want to play with event-based cameras, of course, we believe is a very nice match to neuromorphic hardware. That's available, as well as, over time, other sensor and actuator interfaces are supported through that. And then what we're still building, this has been slipping for quarter after quarter for a while now, with kind of a big system is kind of our lower priority item, but we're getting there, is our big system. So not Spinnaker big yet, but certainly it's pretty big. It's going to have 768 chips, 100 million neurons, basically just extending up this mesh protocol up and integrating all of these chips. It'll be a 5U kind of rack mounted chassis. So stay tuned. Certainly next NICE, we'll be reporting on results from that, undoubtedly. The software, this is the software stack that we have. We scrambled on this last year, and this is very much still a work in progress, and it's it's evolving all the time. But effectively, the principle here is to try to push the levels of abstraction that you as a user have to deal with as high as possible. We've also generalized the idea of, try to formalize the idea of what is it when you define a neural network, a spiking neural network, to be mapped into a Loihi system. It's not just the spiking neural network parameters, connectivity, and all that you normally would think about, but you also have a number of utility functions that go along with that, which really just need to be written in standard code, Python or C or something like that, but have to be closely integrated to the operation of the network. So that could be doing things like data format encodings, decodings, right? The world doesn't generally speak spikes, so you need some kind of encoding, and that's typically a critical part of the algorithm, actually, is how you encode data into spikes. And so that really deserves a first-class citizen kind of status here, right? That the processes that describe all that and maybe orchestrate the operation of the spiking neural network, that has to be placed somewhere in this heterogeneous system. So the SDK manages that, and that's your basic interface. So NXNet is sort of our baseline algorithm that, or API that we expose that gives you access, in a way that's pretty similar to the frameworks you may be accustomed to, things like Brian, Pine, and some of these Nengo type of systems. Still a very low level to anyone who has not been working with spiking neural networks very much. That's not typically the level that people want to code at. So really the frontier of software development and the research really that more activity needs to happen here is in pushing these abstraction layers up. So we're certainly one obvious simple way to abstract this is to just build computational modules that encapsulate some of the magic that's happening that someone else figures out on an algorithm front and then exposes that for other people's use. So we've done that with a series of modules that you can play with once you're part of our network, our community. And then we're also integrating to third-party frameworks, so Nengo being probably the best integrated today, so that if you're familiar with these other frameworks, you can then use them to program Loihi. TensorFlow is an interesting one there because a lot of people, again, with this confusion with deep learning, will assume that, well, why don't you just use TensorFlow? I mean, that should, clearly that's what everybody does, or some other cafe, or PyTorch, or something like that. And the answer is that, well, those frameworks are not meant to be run on neuromorphic hardware. Those frameworks are great for running on GPUs or CPUs, or and they can produce a network which then you can run on neuromorphic hardware. And so that's how we look at it, and that's how we're integrating to these other deep learning frameworks. But you would never literally run, or it just doesn't make any sense to run a deep learning framework on top of a neuromorphic chip. Okay, so to make progress, we've kind of out giving a lot of talks on Loihi, and more importantly, we've exposed the hardware out to a growing community of researchers to try to address these basic fundamental challenges we have in this field, which relate to algorithms, programming, benchmarking, figuring out how we use this great architecture. We believe that there is some value here to be unlocked in this neuromorphic approach, but we're still at the baby steps in terms of actually delivering capability to end applications. So for that reason, we've started this Intel Neuromorphic Research Community targeted at specifically algorithms, applications researchers, wherever they come from, traditional machine learning, deep learning, HPC, computational neuroscience, of course, neuromorphic community, trying to get you all working with this architecture as just an example that we can support for you and work together on finding what works and what doesn't, and try to iterate and make as much progress as we can. So we built this up. We have a process for engaging. You submit a project proposal. In some cases, we can give funding out for academic groups, although that budget is pretty much exhausted at the moment, but we may get more funding in the next year or so. And then we're holding a series of workshops. We're attending things like NICE. We just held a workshop in Portland, where most of my team is based, and we had 90 researchers there. That was a week-long workshop, very hands-on, hearing from all the different researchers what they've done with Loihi, what they plan to do, and then lots of hands-on kind of hackathon sessions of, okay, let's get you up to speed and working. So we encourage all of you to get involved, join, and start helping us take on these challenges. This is just a representation of this last workshop, where people were coming from. It's across the world, everywhere. I mean, North America was more heavily represented than, say, our previous workshop in Iceland, because it was, well, after all, in the US. But we have a lot of European groups involved as well. Not so many in Asia, so we hope to see more participation from there. So if you're interested, this is the email address. We'll come back to this later, just so but take note. This, give us an email, and then we'll send you all a lot more information. We have a website we can give you access to, or we'll have again soon, and tell you how to go through the formal process of engaging. Okay, so now let's go over our results that we've had, and let's go back to that three-circle Venn diagram, zoom in on this interesting region where we have this intersection, recall, with deep learning here, and then we have this new space of interesting new algorithms in region 3. So first of all, we have, you can think of the deep learning as being the low-hanging fruit. I mean, this is where we have a lot of examples to draw from and potentially map, and then we can see, how well does it do. And so, the most simplistic way you can do is just take a straight translation, DNN to SNN, and just use a rate coding strategy, and then just approximate the rate tuning curves with spiky neurons. And Applied Brain Research has done that, and Pete Blau is here, and he's going to be talking about results of one example from that today, which can give surprisingly good results. But then you can go beyond that. You can take backpropagation and actually try to contort spiky neurons into some kind of differentiable form, and then just literally apply backpropagation offline to spiky neural networks. And that class of technique is actually beginning to work and giving some really exciting results there. Now that's offline training. That's not harnessing any of the online learning capabilities, but it is definitely the tool that worked for deep learning. Therefore, it may also work for spiking nets. And then moving beyond that, you can look at some approximations of backpropagation that then do respect locality in the learning rules. And now you can start thinking about actually running some kind of a approximation to backpropagation on the neuromorphic hardware itself. And that is kind of the real frontier. Nothing's really working in that front quite yet, but we can definitely see a number of very productive lines of research that will soon definitely start delivering there. Okay, then we have this region which is say 3.I, let's call it, for kind of inspiration. It's kind of outside of the realm of mathematically rigorous machine learning. It's more direct inspiration from neuroscience, working with people like Tom Cleland and, that we'll talk about later, to say, okay, look, we have neuroscience models of what's going on here. Let's try to abstract it up and just kind of program this in some way into the chip and see if this will work. And there's some interesting algorithms here. This is really where the most creative ideas come from, I would say. And what we want to do at that point then is formalize this, right? Put some mathematical grounding underneath it, so then it goes beyond being just an example to then being a methodology and a tool that can be applied for other things. So that's where we have this like 3.M for mathematical or something. We're trying to expand that domain as much as possible. And in fact, there's quite a few algorithms in this domain here where we have good mathematical foundation. We know exactly what the neural network's doing. And you can just deterministically program this in and get results. And neural engineering framework is a long-standing example of that from Chris Elias-Smith and Applied Brain Research. But other frameworks are rising as well. So solving constraint satisfaction, you saw from Steve Ferber yesterday, we have that running on Loihi as well. Solving graph search problems, for example. Various other things. So here's an example of this first one. You're going to hear a lot more from this from Pete Blau soon. But this is just taking a simple feed-forward neural network, ANN, deep network, train it offline with TensorFlow, give it a bunch of speech input out coming in from MFCC kind of filter banks. So you kind of spatially map some of the temporal correlations in the structure of the data, and just feed it through a spiky neural network that's been basically trained exactly as if it was a rate network. And surprisingly, on Loihi, you can get the lowest energy per inference and any programmable architecture that ABR was able to evaluate. And in fact, I think these numbers, so this is about a factor of 2 lower than the Movidius neural compute stick. And I think that's actually improved. Maybe people give a better number there because we're always improving the software and this speeding up, and therefore leakage is lower and all that. So I think this actually result is a little better. But also what's very interesting is that the scalability. This is performance, so speed, numbers of inferences per second. The orange is Loihi. The blue is Movidius neural compute stick. Both of these are edge devices. This is doing batch size 1 processing, right? Which, by the way, is why these architectures are doing better than, say, a GPU. You may look at this and wonder what the heck, how could this possibly be the case? It's because we're exploring the batch size 1 regime here, where it's real-time inference. You're performing an inference as the data is arriving. You're not waiting to build a big backlog of data, which is what GPUs are designed to efficiently process. You have to engage the big parallel data paths in these GPUs and even CPUs to get the full efficiency. But what we're finding, is as you scale out to a bigger network, this is going from about the baseline network out to a factor of 50 larger or so. You can see the performance of Loihi doesn't degrade barely at all. And that's this fine-grained parallelism you get in a neuromorphic architecture. And similarly, the energy is surprisingly flat here. You know, after you have some baseline energy just from getting the data in and out of the chip, you know, it's very low energy as you scale to larger sizes. In contrast to, you know, even an optimized edge device like the Movidius neural compute stick. So this is interesting. Of course, caveat is that it is just batch size 1, so we can't do batch size, you know, greater than 1 with this neuromorphic architecture. And you did lose some accuracy, you know, 90%-ish versus 92%-ish for the native deep network. Now, is that critically important or not for an application? You know, it's up to you to decide, or an application user. But also, this is, keep in mind, you know, this is just a straight conversion of a DNN to an SNN, right? It's kind of unfair to the SNN because it was not designed to do that, right? Some of these native backprop SNN approaches should close that gap. Now we have another class here, which is no longer a deep learning network, but this is sparse feature extraction, so the LASSO optimization problem you may be familiar with. So this is just a mathematical abstraction here of, or a mathematical objective function that's being optimized. So it's a sparse feature representation where you have some input signal like an image. You're trying to represent it with an over-complete set of features. And you want to do that with as few features as possible. So you find the smallest number of features that best explains that input. It's a convex optimization problem, but a difficult one to solve. It's, you know, it's arguably what's happening in, say, the V1 level of our visual system. Turns out that this has a really beautiful mathematical connection to neural networks, and both rate neural networks, which is kind of illustrated here, with this kind of prototypical kind of lateral inhibition characteristic. So you have cross inhibition between these feature neurons, and the feature neurons are competing to represent the input signal. So the stronger a particular feature matches, the stronger it gets activated, and it suppresses the others that are closely matched to it. So for that reason, it's called the locally competitive algorithm, because there's this competitive dynamic that's happening. And that's happening through this feedback, you know, this recurrent connections in the network. But you can keep pushing the math forward and taking this all the way down to a spiking neural network form. And with full mathematical rigor of knowing then that all of these, the rate-based, the spike-based, all solving exactly the same problem. And the best numerical solvers for this are effectively optimizations of applying gradient descent to the rate-based formulation of this problem. So we have a great case where we can look at the best state-of-the-art solvers for this problem running on a CPU, and compare that, or a GPU for that matter, and then compare that to Loihi. Now, if you look at what's happening in the dynamics of the network as it solves, it's very interesting. You know, I think this is a great example to go through because it shows, you know, this is a rate-based network, basically. You know, you describe the model, the dynamics in terms of rate continuous variables, and yet it has this low-level spiking implementation. And when you look at the spike raster plot here, this is when, so we're reconstructing this image here with this reconstruction with many feature vectors. This is just a sample of the neurons that are most active. You know, you can see that there's this flurry of spiking activity right when you turn on the computation. And what's happening is that there's each individual spike time has great computational significance because the most activated feature is spiking first, and it's then suppressing the other neurons that may have spiked but didn't because, you know, something that matched better spiked first. So you have temporal computation happening in this very first short window of time. And then what happens, it's a dynamical system. So it settles into a fixed point steady state. And at that point, that fixed point corresponds to a roughly, you know, pseudo-random but stable spike rate of all the neurons. So you read the solution out as if it were, you know, rate coded. But the computation happened, you know, in a very, very brief window of time. And you see the objective function, you know, drops extremely rapidly in this very initial phase here. And so when you benchmark that, you get incredible results. So this is much better than the results we reported in the micro paper. This is now scaled up to use the full resources of the entire Loihi chip. And we're finding, I mean, you know, massive factors of difference compared to solving these problems with the Fista solver and the SPAMS package. I mean, this is, you know, the best algorithm for this class of problems with this level of sparseness. So 10,000 times faster, you know, 1,000,000 times lower energy when you run this on Loihi compared to a CPU. This is for a convolutional lasso problem. It's a difficult problem. It's maybe a little unfair to the FISTA solver in this case because it's not a convolutional solver, so we're really thrashing the memory, the caches in this case. You can look at smaller problems, including non-convolutional cases, and you can see that there's just this trend as you go to bigger and bigger problems. The Loihi's gain. This is the gain in speed. This is the gain in energy. Even down in this very simple, small scale problem, we're still getting 10 to 50x improvement in speed and 1,000 times improvement in energy. So here we have a definite example where spikes, and specifically the spikes, are giving really great gains in efficiency, along with all the other neuromorphic architectural properties, but spikes are a very big part of that. Okay, and then moving on from that, we have a bunch of interesting generalizations. We can think about learning now, unsupervised learning the dictionary. So there's a number of threads looking into that, including, I think you'll hear from Yijing Watkins here at NICE on one of these efforts. And also expanding the problem to learning manifolds. So this Senji's Pelavan has a nice paper on arXiv, INRC member, looking at that. Again, just learning in an unsupervised way. And these are all rules that are compatible with Loihi. And then you can stack LCA potentially, and you can maybe use LCA now as a primitive for doing inference in a deep way. And there's reason to believe this will give protection to, say, adversarial attack. And it's learning more natural representations of the data, not just kind of superficial data correlations. Then we also have a class of networks that are coming out of Wolfgang Maas's group in TU Graz that they're calling LSNNs, which are inspired by LSTMs, which you may know give state-of-the-art. We're running short on time. Oh, okay. So you may hear more about these, but LSNNs are running today on Loihi, 94% accuracy on a sequential MNIST result. We haven't benchmarked this yet, but we expect these to give performance and energy characteristics that are much more like the LASSO case than, say, the keyword spotter feed forward, because it has recurrence and feedback integrated in this class of network. So this is the first time spiking nets have given LSTM level results. I've mentioned about the neuromorphic backpropagation class of results. And this is all, I encourage you to check out this if you're not familiar with the work, but this is what's kind of right on the fringe of starting to work in this kind of deep learning class of networks. We've even had robotic arms. This is a result that came from NICE last year, if you were the few of you who were at NICE last year, but otherwise you can actually go look up Chris Elias-Smith's talk and see videos of the demo, in fact, of an actual 6-degree freedom arm that was controlled with Loihi. And the key here is that it's an adaptive controller so that it's able to cope with nonlinear perturbations and friction, and they've modeled this comparing to conventional algorithms, and even the same algorithm running on a CPU and a GPU, finding many factors of improvement, again, in power and performance. We have constraint satisfaction. Steve explained a little bit of this yesterday. Those same problems are run on Loihi, and we're finding very fast operation, solving constraint satisfaction problems like 4-color map coloring and Sudoku, these sorts of things. Solving non-trivial NP complete problems in milliseconds, basically. And let's see, I'll skip over this. This is an interesting graph search problem. Clearly, I have way too much content here. So this is just illustrating the scalability of our Nahuku system up to 32 chips. And you can go over this in a little more detail on Friday as we do our tutorial sessions. But basically showing that we can maintain like 10 microsecond level time steps even as you scale out to 32 chips on a board. We expect to be able to maintain levels like that as you go to 768 chips. So well faster than real-time operation for large networks. And again, we benchmarked some of this for like small world networks, finding factor of 100 improvement in finding the shortest path in a graph in a small world network of a million nodes. Factor of 100 improvement to Dijkstra on a Xeon processor. And the scalability is very intriguing. It's sublinear scaling as you go to larger and larger graphs. So again, it's just a better scalability compared to conventional architectures. And I will skip over this example, but this is Tom Cleland's olfactory system, which is very exciting because this is where we start using the oscillatory dynamics that I mentioned about earlier. But this gives very interesting, compelling gains in accuracy, not just performance and efficiency. But this is because this is some novel algorithm inspired from directly how these neural circuits behave. Of course, you could code this up in some other way. You can run this on a von Neumann CPU, and you would get similar accuracy gains, right? So it's not inherently because it's spiking, but this algorithm was motivated from the bottom up from a spike-based model of how the actual neural circuits are working. And therefore, we can map it right into Loihi. We see these great scaling characteristics. It's performing inference in millisecond timescales, very flat as you scale the problem up larger and larger, just as we're starting to see with all of these algorithms as we map it into the architecture. And then we have the phasor neural networks, which is really the frontier. Not too much concrete to work on this, to report on this. We don't have actual networks mapped onto Loihi other than this olfactory example that I just described. But this is very, very interesting direction to think about in the future. So with all that, finally, I have my final slide. Sorry, I'm too many slides here, but this is where we're at. I think we have a lot of algorithms. We have a growing body of evidence to suggest that there really is value behind neuromorphic architectures, and we can find and we can discover these algorithms that run very efficiently. The challenge now is to really connect these example algorithms to applications and to turn this into really valuable technology that makes a difference that people will actually care about. So, there's some ideas here, but there's still work to be done to really connect these and put this technology out in the real world. Leveraging the strengths and offsetting the potential disadvantage of relatively high cost for neuromorphic architecture because it's integrated compute and memory. Okay, so that's that. I hope you all get involved and email us.
We have time for one short question. Robena?
Yeah, very nice talk, Mike. I have a quick question on how do you map the graph search onto Loihi? Did you explain the algorithm?
Yeah, that's a paper by Hopfield from like 2013 or something, 2006 maybe. The reference is on there, but it's basically a temporal wavefront. It's kind of like a Synfire type of chain where you enable one spike and it naturally, the wavefront will follow the shortest path, and then you first propagate it once through the forward path. It's using plasticity in the network, so it basically records the path that the wavefront followed, so that then you traverse backwards. And this kind of corresponds to processes that they actually see in the hippocampus before, in a planning phase of operation where they observe these backwards flowing wavefronts through the place cells. So it actually has a biological motivation. Okay, and yeah, obviously save more questions for Friday. We have a whole day to talk more.
Thank you again, Mike.